now we're in, and that's great. So we're gonna keep working on chapter 10 as promised. Now, I also emailed the final exam. You probably already know that. So just work on it, and I will say a few words about that final at the end of today's lecture, because what we are doing now is going to be a voluntarily material. So if someone is interested in the chapter 10 stuff, if you plan to continue with more calculus classes, then you can definitely enjoy it. And if not, then we just disregard it. It's not going to be on the final exam. So chapter 10, section 2, I think is very interesting section because it enables us to use our machinery developed, such as derivatives and antiderivatives, to use on nada functions, to use it on various curves in the plane, and we'll see examples. I don't want to just start moving this around, but it could be any smooth curves. And we'll be able to identify the minimum and maximum points as usual. So we're gonna be able to see the lowest local minimums and local maximums someplace, and well, points where this overlap will be questionable. We're not going to have a structure for those, but minimum, local maximums are the ones that definitely could be found using old methods. And the way to be able to solve this type of ideas, the exercises, will be to present our curves parametrically. And to present it parametrically will be presented in terms of two coordinates, x and y. So every point will be a pair x, y. When it's Alex, I'm not surprised. Every point on the xy plane is indeed with coordinate x and y, but they both be functions of t. So it'd be function y of t and function x of t. So there'd be both separate functions. It doesn't fit to put t. I should have used brain before I started to write it. So I get this fixed real quick. So we are gonna get this as a pair of two functions, both in terms of parameter t, or analog of time. It's x of t and y of t, as well as y of t. Try to fit it, doesn't fit. But anyways, this is the point. So, and each coordinate will be a function, again, for some particular examples that we consider, and because of course you can always come up with not functional or not differentiable, but that's not what we're going to care about. And that's what we're going to work on in section 10.2 as well as in 10.3. They nicely go together. So they say coordinates x and y are both separate functions. And that's what we're going to really enjoy here. And in the beginning, of course, they give us some nicer examples. Example of parabola that opens to the right. So you could have probably presented it right away as y is equal to t squared minus 4. So you put x or something, right? So if you start to think of something like x squared minus 4, in this case, looks like it's going to be x squared minus 2, something like that. Then you will recognize right away the graph of function, which is a parabola that opens to the right. So one will say, why do I need these parameters? I could just use the x is equal to y squared minus 2. I should have been careful. So if I take a graph of old favorite parabola, shifted 2 units to the downwards, right? And then if I switch x and y coordinates, I'd be able to get an equation, but the problem is it is not a function. So we should utilize our machinery that we developed for functions, excuse me, to be able to work with it. And the way they doing it, they write it parametrically. So they write y is equal to t over 2, and then x is equal to t squared minus 4. So what they do is they make a picture of portion of this particular curve, and they make a picture in such a way that parameter is going to be bounded by first value of -2 and the second value of 3. So when parameter is -2, turns out you're going to have this point and you will not continue any further beyond value of parameter is equal to 3. Why is that? Well, they just gave you this example. For whatever reason, maybe there is some physical meaning when time can only be in between -2 and 3, whatever. And when they start to calculate x and y coordinates based on this value of parameter, let's say when t is 3, then I can use both of these equations to find x coordinates. So it'd be 3 squared 9 minus 4, which is 5. And then if I put 3 here, 3 over 2 is going to be just 3/2. So this will be the point with coordinates 5 for x and 3/2 somewhere in between 1 and 2 for y. So that's another way to present the same old stuff that we're already working with. And one may ask why Alice they use t over 2. They could have just used t. Yeah, and that way the equation will actually come out. But they decided to divide it by 2, so that's why they got all this little half conversions. But still, so for various values of parameter, you can do the point plot, and then once you produced a few points, you plot them on the XY plane and then connect with a smooth curve and give a portion of that parabola that opens to the right. So the again idea is to utilize parameter in order to show people what is going on, but the key point is to be able to write each coordinate x and y as a separate function with respect to a new variable. And maybe for this example it's not interesting because you better probably use the old approach to write something with relationship x and y, but the new approach enables you to deal with wider class of functions, and that's the point why they want you to do that. So that's the idea. So anyways, this section is just showing you a few examples where they want you to start to get used to this, and basically you can parameterize various functions differently. So you can, for example, here call x coordinate as one function and y coordinate is the other function, and then vary your values of parameter, please notice they have only parameter that greater than -1, you will produce x and y coordinates. And one can say, it looks like, Alex, again, they have a half of parabola here. Yes, so if you try to actually pull out your parameter t, and maybe it's a good idea to do it from here. So if let me do it here, x is equal to 1 over square root t plus 1. So if you be able to pull out your value of t somehow, so how can I do that? How can I isolate t? Well, first of all, I can write that t plus 1, so I flip both sides of my equation is equal to 1 over x. So any way you like to isolate t, then you square both sides. So you're gonna get t plus 1 is equal to 1 over x squared, right? And then you'll be able to actually pull t out. There's going to be 1 over x squared and subtract 1, right? So this is our parameter t that I can now plug into second equation. And one can say, Alex, this is going to be a not very nice looking fraction. Yes, but the point of story is we'll be able to get a function y of variable x, and that's the whole point. So we'll be able to see the actual equation that they have for this curve the way we used to see, not with two coordinates. That's not the stuff that you probably want to enjoy much. So what I'm doing right now, I'm replacing the letter t into the second equation. So t on the top and t now I'm placing here on the bottom. So it's 1 over that minus 1. And then there is also plus 1. So we'll try to simplify a little bit this expression and see what actual function we have here. But notice one thing, we did procedure of squaring both sides. And if you know, when you square both sides, you may pick up extra solutions. Like if you have, for example, x is equal to -1, and when you're gonna, so that's the solution. And when you square both sides, you're gonna end up with x squared is equal to 1, and x squared is equal to 1 also tells you that x is equal to +1. That is not original equation. So -1 also going to work. -1 squared is 1, but +1 squared is also 1. So you picked up like half of extra solutions. And that's why I guess people wouldn't like that. So now what? Well, complex fraction is bothering me, right? So what can I do is, well, I can multiply by x squared and on the top and on the bottom, right? Multiplied by 1 or x squared over x squared. So the bottom part will go away. So what will appear on the top? Well, looks like x squared has to be distributed over here as well as over there. So when I distribute it over the first term, it becomes 1, and second will become minus x squared. So now you recognize the equation y is 1 minus x squared, and that parabola that opens down, right? Minus x squared, and shifted up by 1, so added 1. But please notice that we used to have just a half of parabola, but when we squared both sides, we picked up another half. So I need to make sure I say that my domain is restricted. It is only for the positive values. Looks like the limit for the actual the borderline for parameter is greater than -1, so that's why the point is not included, the endpoint, so x is strictly greater. So the point of story, when you can convert your parametric equation to the just linear or whatever function y of x, then things become much more straightforward because we used to work with this. We're not used to work with that description. But it turns out that that description is convenient in a case when you're not dealing with nice looking functions, because this one we have here is definitely nice looking functions, half of parabola. So previously, I already learned how to operate with it, right? We were dealing with parabolas throughout all the algebra courses, as well as the other course. But what if we have something that we were not used to work with, like the ones on the picture? Let me clean the mess. Stop share, and then I'm gonna share it again. So if I look at the pictures they have here for us, well, this is something you definitely were not working before. When you say, well, that's cardioid, I saw it when I took trigonometry class. Yes, but it is not a function. But the point of story, if it is given with x and y coordinates, and each of them is function separately, well, then you can do integration and differentiation. So you can do those manipulations that we already saw previously. So the parametric equations that we just started to look at could also be differentiated. So turns out that the derivative could be treated as if you divide the two, dy, so y prime by x prime. So if you have separately equation for the x coordinate and for the y coordinate, then if you want to get the derivative dy over dx, or as previously you used to probably write it as y prime, right? When you assumed that function y was dependent on variable letter x. Well, now you need to set this separately. So you need to get dy and dx. So if I take my y prime and divide this by x prime with respect to variable letter t, because now we're given those functions with respect to our parameter. So now I can do finding for y prime, well, using the methods of differentiation we already learned. So variable now is t, so derivative of t squared is 2t. So I multiply it by 16, so that -16, so that'd be -32 multiplied by t. And then there is a subtraction of that 24 plus square root of t. You say, Alex, why did they put square roots? I have no idea. They just give it to you as an example. And that way you will get your numerator. So -32 t's plus that 24 radicals 2 is on the top. And then we'll also get derivative of x and put it on the bottom. So what's x prime, again, with respect to the variable t? Well, it looks like it's just 24 root of 2, right? 24 times square root of 2, like that. So that's our derivative. I say, Alex, you can probably simplify this a little bit if you factor 24 roots of 2 out from numerator. Well, from here is not going to be much fun because it's still going to be root of 2. So I would recommend you to just leave it like that. So this is your derivative of the function. And if you were to actually write function y with respect to x, like I did in the previous examples, so if I pull out the t here and then plug it in there, and then differentiate it, I would have ended up with the same thing. So that'd be the old way, because it looks like the function could be nicely treated as like parabola. Who knows what this is, but some kind of familiar looking curve, not some wavy thing. When you say, so when this wavy, some loop type of structure appears, well, whenever we have trigonometric functions, turns out, then, right, so then you can nicely write this with respect to sines and cosines. So with regular algebraic curves, we don't need to do that, basically. But the formula for derivative is the one that we can utilize from now on. So it's derivative of one coordinate and derivative of the other coordinate. And then we can also use the second derivative. I think it'd be a good idea for me to take a look at this second derivative formula as well as example. And it is something that is, well, not very intuitive. So a little bit different. And that's why I want to look at it. So how to find second derivative? I can say, well, Alex, very simple. Take first derivative and differentiate it again. Yes, you will do it on numerator. So numerator, you differentiate your first derivative. So the one that I just did here, which is actually a fraction of derivative of numerator, I put on the top a derivative of y and then derivative of x. And then I have to differentiate that fraction, but then again divide by x prime, you see? So I put another x prime on the bottom. And I will take derivative of the previous, so it's like a second derivative of that dy over dx. But I need to put in denominator x prime with respect to t. So that's a little extra that is not intuitive. So you would say, well, take my first derivative and differentiate it again. But no, you need to add extra stuff in denominator. And then analogously, you add the extra stuff in denominator if you take the third derivative, but I don't think we need it here because the only application they want to see is concavity. Remember, concave up is here when you have parabola that opens up, that approximates it. And if you have parabola that opens down, then it's going to be concave down. So for concave up, we're dealing with something like positive in front of x squared, for example, so positive values. And for those that open down, we'll have a minus sign in front. So the idea is to take second derivative and see if it is negative, then the approximating parabola is going to open down. And if it is positive, second derivative, approximating parabola opens up. So we can repeat the process once again just for practice. And again, what is this for? To be able to graph. And again, to graph things like this is pointless because you better just rewrite this with respect to t. So I'm doing the exercise wrong way first, just to show you that what we're doing in this particular case is not needed because our parameter t is x squared. So instead of my y, I have a actually function here 1/4. And if instead of t, I put x squared, so that'd be x squared, that must be squared, right? And then if I subtract 4, this is my actual fourth degree function that I can graph without any parametric approach. So it'd be x to the fourth minus 4. So it's a quarter x to the fourth power and minus 1. So we know pretty well how to graph fourth degree parabola. It's just one opens up, but restriction of parameter. Please notice that t may only be positive because square root, you cannot square root negative numbers, right? So it must be positive or 0. That's why it's just a half of this parabola, fourth degree parabola. And once you see it, that's right away becomes familiar. And question is why we do all that? Well, because we're practicing for the worst case scenarios. And if somebody says, okay, Alex, then take worst case scenario and start practicing. And the answer is they don't want to do this because exercises become so nasty. So you will be stuck with them for hours. But they're doable. But the point of story again, that if you had not a function, not something as nice as we see right now in front of us, like a fourth degree parabola, then there is no other way around. So anyways, so if my function x is a square root of t, so I want to find first and the second derivative. So I want to use this new formula just for practice. So first of all, I need to find first derivative, x prime with respect to t, and derivative of square root is 1 over 2 square roots. If you remember that, that's great. If not, just rewrite your square root, excuse me, that's power of 1/2, and then bring this in front. So this take derivative of the power. So anyways, that's my x prime. And then also for y, I have here a quarter in front of that t squared minus 4. So we'll take first derivative as well. And then I'll set up first y prime. So a quarter will still be present. I'm not sure why they factor the quarter out. Maybe I'll just multiply by 1/4 right away. So it'd be 1/4 times 2t, right? And then minus 4 times 1/4 is minus 1, but that derivative is going to be 0. So my first derivative is just t over 2. And then I'm going to set up dy over dx. That's the one that I'm going to differentiate once again on the next step. So dy over dx, or derivative of first one, which is t over 2. So it is a little bit tedious to write, but that's why I don't think I want to test you on this, because kind of questionable if you want to do it if you already know the nice function, right? So, and then you put that dx, which is 1 over 2 roots of t on the bottom. And of course, you want to simplify this. So what you're going to do is flip your denominator. So 2 roots of t will be on the top, right? Over 1 and multiplied by t over 2. So it will be t to the power looks like 3/2, right? And the 2's will cancel. And then I need to set up that fraction. So the fraction that we'll have, so let me write it as second derivative of our function with respect to variable x. Since it's second derivative, they put x squared. And why do they put x squared? Well, because we already had x prime on bottom, and now we're going to have another dx dt, so another dx prime on the bottom. So that's why it's squared, because we're going to multiply the denominator kind of with itself, but it's all canceled. Let's just put this, whatever we found, that derivative here of 2 square roots t, and maybe I'll use another color because to put black over black not going to be visible. So it's square root of t, that's my denominator. And what about my numerator? Well, I need to take another derivative. And that's the idea. So I need to take the derivative the second time. So I have to differentiate the result once again with respect to t. So that will be 3 over 2, right? And t will be raised to the power of 3 over 2 minus 1, which is 1 over 2. Or just square root of t. So I can either write this square root t over 3 over 2 power, or 1 over 2 power. And anyways, I'll write a square root because it looks like there's a square root on the bottom, so it will be bigger too. And that one I will flip, right? The denominator I will flip, so we'll put 2 roots of t next to it, and we'll get, looks like 2 and 2 will cancel, so it's going to be just a 3t. And please notice that's what they actually produced here, 3t. So all that work is done, looks like, correctly. And then what is this for? Well, once we found the second derivative, then we can see if it's concave down or concave up. How? Well, for various values of parameter t, and looks like that will correspond to positive values of variable x, and they actually tell us that x is equal to 2, y is equal to 3, so they just want you to use 2 for x. So if you put the positive values of parameter t, this whole thing will be positive. Put 1 or 2 or 10, any positive number times 3 is positive. So point is, it is going to be concave up, no matter what point you consider with x coordinate more than 0 with positive x coordinates. So point is x equal to 2, okay, so it's still going to be positive, so the result is concave up function at that particular point that they have. And also the first derivative, or slope of tangent line. So the slope of tangent line is going to be positive, and you can actually calculate it. So you can plug into your first derivative, which is the one here, your value for parameter when x is equal to 2. So you can see when x is 2, what's value of t? Well, that's a square root of t. So it looks like it's going to be 4, right? So when x is 2, then to find t, I just square both sides. It is 4. So when t is 4, then we have the value of slope, which is 3 times, which is what? Where is the first derivative? It's here. So when I plug in 4, it'd be the square root 4, 2 times 2 times 2, which is 8. So it is slope equal to 8. So tangent line is here. So the point of getting this tangent line and the concavity is to be able to see what the graph is. We say, Alex, I already have the graph in front of me. Yes, that's why I'm saying it's kind of pointless exercise. That's for those cases when you don't know what the graph is, when you're not working with a nice functions that we already know pretty well how to work with. And so here's example. They work with cycloid, but I read this example and I said there's very questionable how they found things. And I believe I told you that before we had Calc 4 class, and that's where we actually learned everything in details. And here they struggling basically to make sense out of these things because we need really more time to absorb that. That's why I'm making it voluntarily. So what I did, I just cleared stuff here. And I think what would make sense for me to do in conclusion before we say a few words about the final is the other part of the story we learned in this class before, how to find the arc length. And you already know, I guess, that with respect to these parameters, the functions x of t and y of t is not exactly the same. It's pretty close. So when you recall the formula for the arc length, so if you have some function and there is an arc, so from here to here, so they say from value of x0 to value of x1, so you want to find how long this piece is, then you integrate from 0 to 1, and then you take the derivative. Remember, there was derivative, or dy dx squared inside of the square root added 1. So this was the formula that I guess we tried to justify a while ago. And now, if you're going to replace dy dx with those dt ingredients with little denominators, then what you can do here is to use the fact that you will actually have, instead of 1, you can divide the same thing by the same thing. So you can divide dx over dt squared in numerator, as well as the same exact thing, dx over dt in denominator. So when I divide the same pieces, it becomes 1, right? So I could, instead of that number 1, put that fraction in my formula. And now notice we do this in order to have exact same denominator, dx over dt squared, that we already have here, and then numerator will be a little different, dy over dt squared. So that's my right hand. So the point is we ended up with the same denominator, right? And then what we can do is to say that here we have the only dx over dt for the first piece, and for the second piece is going to be dy over dt. If I do what here? Well, so just numerators, and dx over dt will be factor out from that thing in here. So notice that's gonna cancel. Then there's the square and there's no square, just but no square root either. So they will cancel them, and that's how it becomes the dx over dt squared and dy over dt squared. So actually, this is derivative of first coordinate squared plus derivative of second coordinate squared. So I'm trying to give you an idea why this is happening like that. So worth to look at this little algebra. And the point is now we can use this to find the arc length. So they single it out, f prime and g prime. We used to have 1 plus derivative of f squared. Now it is f prime squared and g prime squared. So if you have something to find the arc length, like here's a nice example. So if you have a figure that is really produced by rotating around the center, so it should be indeed some kind of trig functions, right? So trig function, and it has formulas for x coordinate as well as for y coordinate. So if you be able to graph it, and probably your calculator needs to be turned into graphing calculator, into parametric mode. And when you enter this tool into calculator, you can try Desmos, it should work. Then you will get the picture that they nicely provided us with. So the equation is to find the length of this entire figure. How about that? So what they do is they start with observing that everything is nice and symmetric, so they'll just find the length of one piece, and then they take 4 times that piece and produce the whole thing. And the angle they run here will be from 0 to pi over 2. So those are limits of integrations. Again, this is going to be looks like in terms of the angle that they have. So they probably should have put theta, but t theta, similar. So it looks like the formula they want to use for given x and y coordinates, again, somehow they graphed it, and I would say this is what we may be able to see next time, because the graphing of this they don't show. They expect you to use some graphing tools, I guess, but the point is now we can take those derivatives and then we gonna set up the whole structure so the new formula that we looked at will be utilized. So I can try to find first derivative just to verify that it is working. So derivative of cosine is negative sine, so that'd be negative 5 times cosine turns into sine t, right? And then derivative of cosine again, negative sine. So there is going to be a positive sign now coming out. So it's plus sine of 5t, but there is a chain rule. So that will be also multiplied by derivative of 5t, which is 5. So that's my first derivative. And then I need to take the second derivative. Please notice that's not dx over dy, so I don't need the structure like a fraction we did before. I just take a derivative again. So, oh, no, I just need to square it. Yeah, that's dx dt squared. Sorry, got carried away. So now I need to square both sides. Like that. And looks like there you have it here. And then analogously, they take derivative of the second piece. So now they take derivative of sines, they become cosine. So it's 5 cosine, and negative 5 times sine turns into cosine, 5t, and the 5 analogously, because of chain rule, the rule goes in front. So now I need to do some algebra. So now I need to square first, square second, and then multiply it by twice the product. See, that's gonna take you a while to do this algebra. Well, we can actually do it. And the reason why I'm trying to follow through this process is just to show you how you wanna read this math textbook. So to make sure that you understand that we have to get a piece of paper, pen, or pencil and actually go with that. So first squared is going to be 25, right? Multiplied by a square of sine t. And then the last squared is going to be 25, again, square of sine of 5t. And then I need to multiply in the middle 2 times their product. So it'd be 5 times 5, 25 times 2 is going to be 50. So that's going to be negative 50. And then I multiply those two signs. You see what they have here, sine of x and then sine of 5x. Takes a while to write it down, but I'm really happy that I got my computer to work today, because with that other one, it'd be a disaster. I would definitely not do it. So now I do the same thing with the other piece. So when I square it becomes 25 cosine squared. And notice, nice thing is going to happen because cosine squared, because these two can be combined together and give me just 25, right? Remember why? Because sine squared plus cosine squared is equal to what? Remember? Pythagorean identity is equal to number 1, right? So that's why we have just factor this out at 1 times 25. So analogously for the next piece, it's also going to be minus 50, but now the product of two cosines. See, now they start to use trigonometry. So that's why I decided to trace this, because it may not be obvious to some people. And now here we also have 25, but it's cosine squared, and as in the beginning of this, it's also going to be converted to something nice, to number 25. Because again, it's sine squared plus cosine. And what's in the middle? Well, they just copy these two together. I say, Alex, but what happened with their 25s? Because looks like they have just a 2 in here. Yeah, that's a good question. Looks like they factored out. Notice they were able to take out 5 and put it in front. So they have just 25 square root is 5. So they used to have 4. And when they square root 25, you get 5. So that's how they got their 20. You see? See, they just scrambled so many steps together and ended up with adding just 1 and 1. And that's how they got that 2. And these two pieces. So what happens there? So the 2 is factored out. And now it turns out the sine plus cosine is going to be cosine of what? Looks like they have a half sum. So they ended up with cosine of 40. That's another trig identity. I say, how do I know all that? Well, at the back of the textbook, you'll be able to check out the formulas, and the one they have is and sum to product formulas. And I guess I'm not gonna go there, but you'll be able to check and see sum and product formulas for the sum of sine, and cosine. So that's the idea. So you can verify if you want. So that will be 1 here. And then it turns out that's a half identity. So you end up with 2 sine squared, again, another trig formula. And that will be possible to extract the square root because they're 2 perfect squares. When you say, is it really possible? So they started with such a nasty expression, and then they were able to nicely square root it. Is that amazing? Yeah, they gave you on purpose this nice question, because otherwise you'd be totally stuck with this trig story. And then you integrate sine and it becomes cosine. Derivative of cosine is negative sine, so that's why the minus came out. And then you plug in upper, lower, and you get done. So as very briefly, I tried to touch the story of parametric equations and differentiations, and that's actually a couple of examples, and that concludes. And next time, I think I will discuss more of trig, and that will be polar coordinates. So besides parametric coordinates is polar coordinates, and that's what I'm sure you saw in your trig class. So that should be something familiar, but that's what they were using in the section 10.3. So next time I plan to say a few words about 10.4, and in the meantime, I want to refresh your memories that I emailed you the final. So I emailed you the final that has 2 questions, just like a midterm. 2 questions, and you should use your last digits of student ID to put in and to, I guess, do your best to show work. And one of these exercises clearly says it's a L'Hopital's rule, so you can just use the L'Hopital's rule. And I believe the hint is you utilize the fact that if you have the function y, you can write it as ln of e of y, the power of y, something like that. So this way you could use the power rule to put this power down, and then in the case you want to utilize this L'Hopital's rule approach that we took. So utilize logarithms. So you can check out that section with L'Hopital's rule. There's a bunch of exercises that I did last time, and last time it was a while ago when we were in that section. So applying logarithm enables us to take derivatives, so then you will be able to differentiate it, and then utilizing the L'Hopital's rule when you differentiate in 0 over 0, infinity over infinity. That's why it says L'Hopital's rule. So that there was method used for a few exercises. So you can check that lecture and if you forgot. That's why I gave it to you earlier, so you can, first of all, do some homework on that section, maybe a couple of problems for practice, and then you will be able, I'm sure, to do it because it's pretty standard question, L'Hopital's rule. And the other one is series, and we worked with series for a while, and you can use any method you prefer because we had various tests for series, so you can use any of those, up to you. Just show what you've done, and I'm sure you will get a good results. And if something is going to be still unclear, well, next week on Tuesday, when technically the final is scheduled, I will be, of course, again on Zoom. We'll discuss a little bit more of chapter 10, and I will also be able to look at your question if something is unclear and give you some hints. Because again, the goal of final is to make sure you get a perfect grade, right? So I will do my best to help you. And if something is unclear, I will clarify it. So don't hesitate, ask. Or I'm sure some people already be done by next week, Tuesday. So just email me your work. And don't forget to also please email me homework. That'd be great. So that way you will support your perfect grade for this class. And I guess that's all I wanted to talk about. So if you have any questions, please ask. I'm going to stop recording at this stage. So I will do more of chapter 4. The plan is to maybe do 10.4, maybe 10.5. We never go further than 10.5. So I think we're in a good shape. So next week I will look at a couple of more sections of chapter 10. Again, they're not going to be for the exam.